Some time ago it was determined that energy is proportional to frequency, but around 1900 it was determined that not only is it proportional, but you get to the point where you get individual energy packets, meaning the energy itself is quantized. There's a particle of energy at which point you cannot get any smaller. We call that a photon. And this is known as Planck's constant formula. The energy is proportional to frequency, but only when you multiply it times Planck's constant can you see the energy of individual photons. And look at the incredibly small size of this, joule seconds. So if you take joule seconds and you multiply it by a frequency, which is 1 over seconds, you will get joules. We can use this to calculate the energy of all sorts of stuff. Say a photon of infrared radiation. Well, there's your wavelength. We need the energy, but we can do wavelength to frequency. We can do energy to frequency, but you could combine those two formulas. Here is the speed of light equation rearranged for frequency. Therefore, you plug that into what frequency is right there, and you get a formula that allows us to directly get energy from wavelength. These are interestingly both constants. Do you see that? So that constant times that constant divided by the wavelength that was given, but watch out because it's in nanometers, so we'll convert that into meters. You could always say, 500 times 10 to the 4th times 10 to the minus 9th meters. Ooh, that would be ugly. It's better to do it the way you see it. And there it is, giving us a very small amount of energy. Similarly, for an X-ray, we should get a larger energy since it's more dangerous. And we do. 6 orders of magnitude higher. And this is Planck's constant.